Click the bell icon to get latest videos from Ekeeda.
Hello friends, so today we are here to learn about the eigenvalues and eigenvectors. We have seen what is eigenvalue and eigenvectors. In this particular video, we are going to focus upon the relationship between every particular matrix A and its eigenvalue, and what are the different types of matrices and their respective eigenvalues. So eigenvalue or characteristic value or latent value of any matrix A is termed as when we multiplied the respective eigenvector with the matrix itself, which is A into capital X, is nothing but lambda into X. The same result it gives when we multiply the eigenvalue with the eigenvector. Let us understand this. Suppose we have got A matrix and it has to be a square matrix of order n by n. So A into its respective eigenvector X is nothing but the same result it produces when the same eigenvector gets multiplied by the respective eigenvalue. That means when we are multiplying A with the X, with A matrix with the X, which is the eigenvector of the matrix, the same result it produces when we multiply the same eigenvector with its respective eigenvalue. That means we can literally replace this A by eigenvalue. Now eigenvalue is just a number, 2, 3, 4, 5, minus 6, like that, but A is a matrix. So eigenvalue, every eigenvalue has the power of replacing the same matrix by its own value. So let us understand this by processing further. Ax minus lambda into X. When we take this particular value on the left hand side, we also check for whether we are going to multiply with the matrix or not, because in this particular case we have got matrix into matrix. Here we have got eigenvalue into matrix, but in order to have the same result characteristic wise, we need to have A into X on the left hand side and lambda into X, which is nothing but the eigenvalue, and which is going to be 2, 3, minus 4, minus 5, minus 6, like this. So in the left hand side we can see one matrix gets multiplied with another, and one matrix we have and another algebraic value it gets multiplied with. But in order to have the same result, we can have one matrix which is I, which is same as multiplying with 1. So we can have lambda X into I is equal to O. Now this is not 0, this is the null matrix which is O. Now from here we can have A minus lambda into I into capital X and O. So clearly from here we can have A minus lambda I into X is equal to O. Now clearly when we have A into B is equal to 0, what we can say is either A is 0 or B is 0 or both are 0. But in this case we can see A minus lambda I into X is equal to O. Now we can either have A minus lambda I is equal to 0 or capital X, that is eigenvector, has to be 0. But friends, we cannot have eigenvector as 0, so we can have this particular term is 0, but therefore we can have mod of A minus lambda I is equal to, now this is 0, now this is not O. In this particular case when we multiply this matrix we can have O. In this particular characteristic we can have determinant value as equal to 0, and this is the characteristic equation which we write. Characteristic equation. And this is how we arrive at certain points, like the analogy between algebra and the matrix. In algebra we have 1, in matrix we have I. In algebra we have 0, in matrix we have O, that is null matrix. and I is nothing but the unit matrix with all the diagonal elements are 1 and all the other elements are 0. In this particular case, when we talk about inverse, which is A inverse, we can have reciprocal as the analogy. When we have x, we can have A. When we have 1 upon x, we can have A inverse. So all these analogies will apply and will derive at few results. So let us understand the matrix and eigenvalue. So we are going to have different types of matrices over here and the respective eigenvalue. For consideration, we are taking matrix A and the respective eigenvalue as lambda. As we know, if we have A square, then we can have eigenvalue as lambda square. If we have got A cube, then we'll have lambda cube as its particular eigenvalue. Now, in general, I can say if we have A raised to n matrix, that is, matrix A is taken n times and multiplied with itself, we get the result as A raised to n. So, the corresponding eigenvalue is nothing but lambda raised to n. So, in order to have the inverse, which is the reciprocal, then that is the analogy between algebra and matrices, we can have A inverse over here. So the lambda, that is the eigenvalue of every inverse A, is nothing but 1 upon lambda, which is the reciprocal, because inverse and reciprocal, these are the analogies of this same. Now we can have A bar, which is nothing but the A conjugate, the conjugate of matrix A. We can have lambda bar, which is nothing but the conjugate value of the eigenvalue lambda. When we have A raised to theta, which is the conjugate transpose or transpose conjugate, then also we can have lambda bar, which is the conjugate value of lambda. In case of transpose of the matrix, only rows and columns are getting interchanged, so the value of the eigenvalue remains unchanged, which is the lambda. In case of Hermitian matrix, we can have all real values. In case of skew Hermitian, we have Hermitian matrix and the eigenvalue is real, but in case of skew Hermitian matrix, we cannot have real, we can have imaginary eigenvalue. If we have k into A, so we can have k into lambda as the eigenvalue. When we have adjoint of A, which is very important, adjoint of A, then we can have modulus A, which is determinant A divided by lambda as its eigenvalue. So this was all about matrix and the eigenvalue and the relation between them. Thanks for watching this video. Stay tuned with Ekeeda and do subscribe to Ekeeda.